Hi, this is Lab 11 on diffraction. I'm Oliver.
I'm David. Alright, our setup consisted of a laser, a collimating lens, an aperture, and we imaged it onto a camera. We calculated the distances at which the Fraunhofer region begins, which is given by a Fresnel number less than 0.01. This is assuming collimated light with a converging lens. These numbers reduce. Moving from an image of the aperture, we moved back into the Fresnel region and we saw a pattern with vertical fringes. We moved further back into the Fraunhofer region and we saw a diffraction pattern that behaved like the sinc squared function. Here we used 4 different single slits of varying sizes, and we saw as we increased the width, we decreased the mode spacing. For the double slit apertures, we saw that as we increased the separation, we increased the frequency of the interference peaks. For the 80 micron slits, we saw the frequency of the envelope increase compared to the 40 micron slits. As we increased the separation, we saw the frequency of the interference peaks increase as well.
We looked at 4 different complex aperture shapes. This one is a circle, and we saw strange diffraction in the Fresnel region and regular diffraction in the Fraunhofer region, which I'll describe later. This is the Fresnel and Fraunhofer regions of a rectangular aperture, of a square, and of a triangle in the Fresnel and Fraunhofer regions. We looked at the Fraunhofer diffraction of a rectangular aperture in MATLAB. We took the intensity data and plotted it and scaled it to a sinc squared function. We found that the first minima and the second minima matched the known values for the sinc squared function. We also looked at a circular aperture and found that it matched a sombrero squared function. We were slightly off on our first peak, but our second peak matched the predicted values. In the circular function, we found that the peak was not evenly spaced between the 2 minima, but the rectangular function was evenly spaced between the minima.
For the additional question, we have car headlights far from the lens corresponding to diffraction in the Fraunhofer region. For small angles, we used the Rayleigh criterion to calculate the max distance from the lens in which we can still resolve the 2 headlights. Assuming a headlight separation of 1.5 meters, a wavelength of 500 nanometers, and a lens aperture of 50 millimeters, we found this distance to be 61.5 kilometers.